Yeah, so thank you for having me. I'm like Emanuele. I'm also sad that I'm not there. I would say I'm sorry, but I'm more sad than sorry. So I'm going to tell you about cosmological measurements of neutrino masses and other relics. And these are two very big topics. And I'm just going to say things about them. And I hope these are going to spark discussion, and we can talk about whatever you, the audience, are more interested in. So I'm going to start with very quick, brief summary of the temperature in the universe, starting all the way on the left with inflation and reheating, which could happen at energy scales as large as 10 to the 14 GeV. And as the universe expands and cools down, it goes through interesting phase transitions. The ones that we care about for this talk are three: the QCD phase transition, BBN, and recombination when the CMB is emitted. So QCD happens at about hundredths of MeV. BBN happens at about an MeV. That's when protons and neutrons combine to form nuclei like hydrogen, deuterium, and helium. And at about temperatures of 1 eV, you get recombination. Protons and electrons from neutral hydrogen that you will be able to see one day with PUMA and with other 21 centimeter experiments. And when you get to today, you have like 10 to minus 4 eV temperatures. So this is about 1 Kelvin. From this, we actually have some messengers of when some of these transitions happened. So for recombination, we have the CMB. So there's a background of radiation emitted, which is photons that gets to us. Whereas right before BBN, at temperatures of about 10 MeV, there was a cosmic neutrino background that was emitted. And we've actually seen this cosmic neutrino background indirectly in experiments and cosmological experiments. And the new physics questions you can ask is, what is the mass of these neutrinos? It's well motivated, it should be there, but we have no idea what it is. But you can go even further and ask, can there be other new particles that decouple at some point in this whole thermal history between an MeV and like reheating? And if these particles are light relics, which means they decouple while relativistic, they should survive until today. They should be pretty much like neutrinos. And they have large number densities, large energy densities, and they affect the evolution of the universe. So you can use cosmology to go after them. And this requirement of decoupling while relativistic is actually fairly generic. So when you go to the earlier universe, densities are larger, temperatures are larger. It's easier for particles with low masses and weak couplings to be coupled and then decoupled and to survive until today. So these are the two questions that I'll talk about, like how to measure neutrino masses and how to look for new particles. And to give you a more fun idea of what the numbers are for these things, here's a plot of what's the temperature of a relic that would be today versus the temperature when it decoupled. And the temperature when it decoupled matters because once it decouples, it stops talking to us. Whereas the standard model of photons and everything that's coupled to them keeps heating whenever degrees of freedom disappear. So particles with an earlier decoupling to the left talk to more degrees of freedom at the time, so they will be colder today. And you can see in this purple line how particles that would decouple at very low temperatures will have the same temperature as the CMB, 2.7 Kelvin. Before the E plus minus annihilation, it's about 1.95 Kelvin. And then when the QCD phase transition happened, there's another big drop in the number of degrees of freedom. So the temperature goes lower and eventually reaches a plateau. And this is for temperatures high enough for which we have counted for all the degrees of freedom in the standard model. They could also, of course, be more degrees of freedom, but as far as we can tell, this is as low as it gets. So if there was a relic today at some point, if there's a relic at some point, its temperature today would be from 0.91 Kelvin to 2.7 Kelvin. And again, a great example of these relics are neutrinos. We know that they decouple at about 10 MeV. So the temperature is about 1.95 Kelvin. They live here. You can also go look for anything else that decouple at some point, and you can parameterize it by its temperature today. And I'll talk about later how that relates to an effective, which is the quantity that we actually physically measure. But first, let's talk about neutrino masses. And I'm not going to give a super in-depth review of what neutrino masses do in cosmology, just to give you an idea of how we measure them and how we can improve. So this is the usual standard plot that you see when people talk about neutrino masses. is in the y-axis the sum of the neutrino masses, which is what cosmology cares about. And on the x-axis, the mass of the lightest neutrino, which we don't know yet. And laboratory experiments typically put limits on this at about 1 eV, so to the far right of this plot for now. So given what we know about oscillation experiments, which is the splittings of 2 of the masses, we can tell that at least 2 of the neutrinos have masses, but we don't know the mass of the lightest, and we don't know the ordering of these masses. So it could be the normal ordering or the inverted. But either way, even in the most pessimistic case of entirely massless lightest neutrino, they predict some sum of neutrino masses here. There's about 0.06 eV for the normal and 0.1 for the inverted. And given the temperature of the neutrinos that we know, so it's 2 Kelvin, give or take, these particles should become non-relativistic at some point in cosmic history at about redshift 30 to 100. And this is important because once the particles become non-relativistic, they become part of the cosmic matter density and they affect the evolution of structure. And it is something we can measure really well in cosmology. So you can ask, why use cosmology rather than lab? And the short answer is that there's a lot of neutrinos in cosmology. You can roughly calculate number of densities to be the ratio of temperatures cubed to the photons, about 10 to the 2 per centimeter cube per neutrino. So it's a fair amount of them. They carry a large amount of energy density in radiation in the early universe. And if they become non-relativistic, they also carry some amount of energy density in their mass nowadays. So the energy density, which is number density times mass, once they're non-relativistic, is about 1% of the total matter for neutrinos of 0.1 eV mass. So of course, if you have 3 neutrinos, it's the sum of neutrino masses that comes in here. And this is actually something that will affect significantly evolution of structure, because 1% of matter will be dark matter, but not cold like we're used to. And before I get into more details, I'll say that you should go and read Julian and Sergio's review from 2006, because it's 15 years old, but it's aged like a fine wine. So what do neutrino masses do? Well, CDM and baryons cluster at all scales. So whenever you have a power spectrum, whatever it is, say it was flat in our toy model, CDM and baryons just trace this power spectrum because they have no initial velocities. Neutrinos do not cluster at all scales because they have temperatures, they have momenta. So their typical velocity is given by their momenta divided by mass, so temperature over mass. So these things are moving around in the box. And this gives them a free streaming scale, which is roughly given by the Hubble times their velocity. So how far they've been able to travel in a Hubble time. And this means that scales below some wave number, which is the inverse of this length, do not cluster. The power spectrum is suppressed. And the fact that they don't cluster means that the power spectrum will change, but they will, even if you were looking only at the cold dark matter and baryon component, their growth of structure is slower. And that's because neutrinos contribute to the overall expansion of the universe to h of z, but they do not contribute to the clustering, to the Poisson equation. So even if you were just looking at the black line, it will be suppressed in this regime. So neutrinos behave like hot dark matter. And we can use this to measure the mass of neutrinos, to measure when they become relativistic and how many of them there are. You can even see this by eye. There's a simulation from this paper in 2010, where you see in the left, you have cold dark matter with massless neutrinos, and you get like all this Lasker structure of the universe, beautiful filaments, galaxies, and so on. And on the right, part of the dark matter is neutrinos at 1 eV mass. And you can see how all these super dense clumps have actually gotten erased, and you get a much more homogeneous universe. Of course, we don't rely on seeing things by eye. We do careful perturbation theory, we model these things, and we look for them in data. So you can ask, in which probes do we use to measure clustering? And this is a cartoon of a non-full collection, but a relevant collection of probes that measure the clustering of matter at different scales on the y-axis and different redshifts on the x-axis. So at redshift 1000, you have the CMB. Importantly, the CMB is lensed on its way to Earth. So this gray square over here is a CMB lensing. So the CMB is weakly lensed by inhomogeneities on the way. And these measure matter power spectrum on much lower redshifts and relatively high K. So these are very important to measure neutrino masses. You also have Lime Alpha Forest, You have galaxies, which for now they cover this red square from SDSS, but in the future this will expand. You'll be able to do much better with photometric spectroscopy surveys and things like PUMA. And then in blue, you have weak lensing surveys, which measure just the matter fluctuations directly without galaxies by seeing how the galaxies are lensed. And by the way, anything above this black line will be deeply nonlinear. So it will be very hard to model. Although, of course, nonlinear corrections can happen below this plot as well. But neutrinos, given what we know about their masses, should free stream at about these scales. So anything above this gray band should be affected by neutrino streaming, which is pretty much everything in our cosmological observables. So we can use all of this data in principle to learn about neutrinos. And to talk about this holistically, I'm just going to give you an update of how far we are in measuring neutrino masses with cosmology. Planck temperature alone doesn't do extremely well. That's because when you go to this plot, you see that CMB alone, neutrinos hadn't started free streaming. They were relativistic still. So a lot of these effects of the neutrino free streaming, you don't really see in the large-scale structure because you don't have large-scale structure data. So Planck temperature alone doesn't do great. Once you add polarization and lensing, the D is for deflection, you actually improve by a factor of 2 or 3. You start closing in. And if to Planck you add temperature, polarization, lensing, and BAO data from galaxy surveys, you get really, really tight constraints on the neutrino masses. I believe the number is at 0.12 EV. So this is getting to the point that we're starting to disprefer the inverted ordering over normal, which laboratory experiments do as well, apparently. But the question that I have in my mind is, in the future, say we get a measurement, where is it going to come from and how robust is it going to be? And we know that there's going to be different low redshift surveys, like DESI is running already, is the successor to SDSS, which is a spectroscopic survey. The Vera Rubin, which used to be called LSST, is photometric, which will do lensing and other things really well. And on the CMB side, you have Simon Observatory, CMBS4. So at some point, we hopefully get a measurement. And there are different theoretical things that we have to worry about. One of them is galaxy bias. This is from a paper by Emanuele in 2013, where they found how to correct for part of this bias due to neutrinos. But there's still something that we have to account in our models and we've worked on. And I'm going to show another plot from Emanuele's talk, which is this. You've seen this and how it relates with the 21 centimeter part that to be able to measure the optical depth organization and break a degeneracy with MNU. And I want to sell it to you not just as a way to break degeneracies and improve constraints, but also as a robustness check. The optical depth organization has changed a lot over the last 10 years. This green band is what WMAP measured in 2013. In orange is what Planck 2015 measured. And in red, what our best constraints from Planck 2018 now, which goes to the far left of this plot. Since the optical depth is one of the main obstacles to measuring the sum of neutrino masses, we should really find ways to marginalize over it appropriately so we don't get the wrong neutrino masses. So that's what I wanted to say about neutrino masses. And I'll talk a little bit about other relics in cosmology. As I said, just like for neutrinos, the number density goes as temperature cubed. So depending on when they decouple, you can figure out how many there should be today. And if these things are relativistic at all times, if they're exactly massless, you can calculate the contribution to the radiation energy density of the universe through this number N effective. So radiation is proportional to the radiation in photons. With this N effective accounts for the variation around us. This should be about 3 in the standard model. So any number that is not 3 is telling you that there's something else more than neutrinos. And the contribution for a relic, I'm showing here on the y-axis, is just the number of degrees of freedom times temperature to the 4th. So the purple line here corresponds to a scalar. So Gx equals 1. And you see, as you make the temperature lower and lower, the N effective becomes smaller and smaller. It goes from order unity here to about 0.027 at the very bottom. So this 0.027 is this target of futuristic experiments, both CMB, large-scale structure. If we can put our error bars well below here, we can test that there was nothing minimal added to a standard model. And you can, of course, you could add things and then add enough degrees of freedom that the bottom line keeps going down and down and down, but that's fairly non-minimal. So something good and interesting about an effective is that it captures anything that is light enough. So it has to be that these particles are relativistic whenever you're looking at them. And for the CMB, that means that the mass has to be below 1 eV. That's roughly they're going to be the temperature of the CMB. If you look at BBN, it's going to be about 1 MeV. And the way that an effective affects these eras is by changing the energy density or changing the Hubble expansion rate, which at the BBN, that changes the abundance of primordial elements. At the CMB, the effects are more complicated, but essentially they amount to the same thing. You're changing the expansion rate at the CMB. And this is something that you can go and see and understand when looking at data. So here in this plot, the authors show the data from Planck in the black points, and the green is a regular prediction of lambda CDM, which is 3 neutrinos. And by the way, here the data are undamped just to show them more horizontally, but this is the regular CMB that you're used to. And as you increase or decrease the number of neutrinos, you change the damping tail of the CMB, and more neutrinos produce more damping. Whoop, sorry. And well, as Emanuele said, there's a big degeneracy with this damping with the helium abundance. So you can fix the damping tail by changing the helium abundance, and these lines get much closer, but still they're different. So this is how the CMB goes and measure the neutrinos. You can run your entire CMC, and the best limits from Planck currently are at like 0.2, more or less, a 95% confidence limit. From BBN, they're comparable. They're like around the same level, but as I say, at 1 MeV with entirely different systematics and uncertainties. So we can essentially rule out anything that decoupled after the QCD phase transition. But before that, it could still be there. And the hope is that CMBS4 experiment or things like it will be able to bring this down to the 0.02, 0.03 level. So that is hopeful because we'll be able to probe much more of this parameter space, find new particles. But this still tells us that at the very bottom, this very lower prediction will be measured at 1 sigma at best. So either we'll get a hint that there's a relic, or we might not even see anything at all. And we'll still not be able to rule this out at enough significance to convince ourselves there was nothing in the early universe. So something interesting you can learn is what happens if the relic isn't massless. And as I said, for the case of the CMB, that means what happens if its mass is comparable to its temperature at the CMB. So if its mass is about 1 electron volt or so. And we call this light but massive relics. And I'm going to tell you about the search for these that Linda Xu led, who's a postdoc at Berkeley. And the idea is, instead of looking at the 1D plot of just temperatures or ineffective, let's also expand it by looking at their mass. And we have no idea what's happening here. We know for neutrinos should be somewhere at 2 Kelvin, and we don't know their mass. But if you have a new particle, where do they live? The interesting thing, that the reason you win with cosmology in this is because you can do spectroscopy for the new relics. Just like for neutrinos, we know that these relics will free stream if they have a mass, and the free streaming scale is given by their mass over temperature. So just, again, their velocities. And the amount of suppression that you get in the power spectrum, which is what I'm showing here, the suppression in the power spectrum, is proportional to their abundance, which is mass times temperature cubed. So if you had infinitely good data, you'd be able to measure both their mass and their temperatures independently. And you'll be able to tell not only that there is a relic, but also some of these properties. Now, before you get too optimistic, all these curves have masses in the range of 2.5 to 3.5 eV, and they're not all that different. So like the kind of constraints you will get on their mass if you saw one of these relics would actually be moderate, but that's better than just saying there's a relic, I don't know its mass or its coupling or anything. So this is a scan for lemurs using our best current data from galaxies, weak lensing, and CMB. And what we find so far is that there are no lemurs in data. So once you marginalize over lambda CDM, neutrino masses, which again would be a lemur of a kind, you find that there is no relic. These are the best limits that we can set. So anything in these curves is allowed a 95% confidence limit. I know this is the opposite of the usual particle physics convention where you plot the rule out thing. And then looking at this plot, you can ask, what is the maximum temperature that is allowed at each mass, and what is the maximum mass at each temperature? So looking at the maximum temperature, the interesting point is at very low masses, you recover the N-effective bound. So N-effective of 0.2 from the CMB corresponds to a temperature of 1.3 Kelvin, more or less. So when the mass is 0, the CMB is setting the N-effective constraint. But as you make the relic heavier and heavier, you start deviating from it, and you start getting deeper and deeper constraints, so more stringent. So that means that relic with a mass have an effect on the large-scale structure that we can go and search and allows us to distinguish and look for them better. So it's an improvement over N-effective. This is even below the target of 0.91 Kelvin that I mentioned, this lowest temperature. So at some point, we're going to be ruling out relics above some mass. And so we actually did a dedicated search for different light but massive relics. And we just crossed that characterized by their spin. So you can have a scalar like an axion, a vector like a dark photon, a Val fermion like a gravitino or a sterile neutrino, and a Dirac fermion. All of them, again, at this minimum temperature of 0.91 Kelvin. And these are the limits that we found. I'm not going to show the scalar because the limits are very weak. They go up to 10 eV. So the data doesn't seem to want to rule out a scalar. But you have all these limits for all these particles. And the case that is perhaps the most interesting is the case of the gravitino. The gravitino would be a Weyl fermion. And if it was stable and the last relic to decouple from the SUSY sector, it would actually be at 0.91 Kelvin. And using our limits, we can say that the gravitino mass has to be below 2.3 electron volts. And that is about a factor of 2 stronger than we had with the CMB before, and almost an order of magnitude better than we did with Laminar alpha forest 10 years ago. So using a lot of these data complementary really helps set the best limits on relics and anything else. I want to spend a minute or two talking about other relic origins. So they don't need to be exactly in thermal equilibrium with the standard model in the early universe. There are many other ways to get things that look like an effective, with or without a mass. One of the ways is through PBH evaporation. So in this paper, the authors say that we have primordial black holes with very low masses in the 10 to the 5 to 10 to the 10 gram regime. They can overclose the universe and they Hawking explode, reheating the universe. And they will Hawking evaporate to everything in the standard model, plus any new particles that may or may not couple to us, as long as they couple to gravity, which they should. So you actually get an effective from this sort of behavior, and it depends on the mass of the PBH. You can have Fermi pressure giving you something to look like a relic. So you have a fermion, and they have very small mass, very large number density. Their Fermi momentum looks like a temperature in a way. It redshifts like 1 plus z. So it makes these particles relativistic at early times, and it makes them look like pretty much like a neutrino or one of these lemurs. And you can have other things like unnaturalness, when you populate a bunch of sectors and the light relics from these sectors may get populated and also affect the universe. So how did Emanuele call it? My propaganda plot is a theory propaganda plot, which is to actually look in 2D space for relic. Look broadly. Don't just look at an effective if you have to. Just search for any possible thing that may show up in cosmological data. And we know how to populate this really well. And we know cosmology is the best place to look for this type of relics. And that is because these things will be very weakly coupled and will be very abundant in the universe. So cosmology is really the natural place to look for them. We know neutrinos have a well-known temperature, 1.95 Kelvin, and we've used cosmology to set limits on their mass. And for now, we only have limits. And I think an interesting question to ask, and I want to bring this up to the discussion later, is how do we convince ourselves using cosmology that we measure neutrino masses? And the reason to ponder that nowadays is because as the cosmological limits get deeper and deeper, it's possible that they get a detection before laboratory do. As I said, Katrin right now sets limits at 1 eV, more or less. In the future, it will close to 0.2, but this is still far from, a detection here. So once cosmology comes and gives us a number, what test do we have to do to convince ourselves that we've measured neutrino masses? I've also told you about a new physics example, which is the gravitino of a new relic. we know its temperature, we can constrain its mass, and this has implications for SUSY models. But again, broadly, the question that I'm more excited about is, are there other lemurs? Are there any other relics populating our universe, which may or may not come from thermal contact with our universe? So that's what I wanted to say. Thank you.
Thank you very much, Julian. So questions? I have one. So for the gravitino bound, are you assuming, so I'm a little bit confused by your assumption. So are you assuming only standard model degrees of freedom in the thermal bath, say? So there is no other SUSY particle, say, when the gravitino decaps?
That is right. We're assuming that is the last thing to disappear in the SUSY sector. So the only degrees of freedom to disappear after it decouples are standard model. And that is, in a way, a conservative assumption. The gauge-mediated SUSY breaking scenarios usually have it, there's some vector boson that decays to it or something. I'm not sure the details, but they usually has a higher temperature than 0.91. So in like these limits, this CMB limits actually had a slightly higher temperature. So they decouple, so the gravitino decouples slightly after the top has disappeared.
So sorry, I mean, just to clarify, so this bound is the worst possible or the best possible?
The best, the most conservative.
So the best possible in your
the most,
conservative.
The most,
I mean, conservative has two meanings. So it's like the stronger constraint that you can get on the mass, or the weaker one.
It's the weaker. It's the weaker.
I mean, do you assume you don't have a gravitino problem, right? Do you assume that you reheat the full SUSY spectrum, or
we do not? As long as the gravitino decouples after the SUSY particles have disappeared, it doesn't matter to us.
Yeah, sure, but okay, I see. So if we would decouple when there are still SUSY particles in the plasma, the constraint will get weaker. Correct?
That is correct. That is correct.
Thanks.
Yes.
You can just unmute yourself.
Yes, thanks, Julian. So can I ask, how much worse do the constraint on neutrino masses get when you marginalize over light relics? Do they degrade like a lot or not?
They degrade some. I'm not sure I could tell you if it's a factor of 50% or 100%. We might have an ellipse. I might have an ellipse somewhere. Let me see if I can find it. I have an ellipse. Oh no, I might not have an ellipse, sorry. I think they do degrade somewhat, like maybe 50% to 100%. But not, I mean, these are different temperatures, so the effect of like this, the effect of the suppression happens at very different scales.
Well, I guess you can still measure neutrinos because they will, I mean, at least they are still relativistic at CMB decoupling, right?
Correct.
So,
correct.
So you get them from an effective a lot also there.
That is right. But even if you look at this sort of plot that I showed for the free streaming scale, the neutrinos have temperature of 2 Kelvin, the relics have temperature 1 Kelvin or more or less, the temperature about the same. But the masses of the neutrinos are much lighter, like 2 orders of magnitude lighter. So all the free streaming scale happens much farther to the left for neutrinos, which is part of the reason you can do well with relics, because the free streaming corresponds to scales within the actual range you measure with galaxies, rather than larger scales.
Thank you.
Sorry, they degrade by about 10%. We have a theory plot in our first paper where my student Nick De Porcio was leading. So if you have a relic present, the neutrino mass will degrade by 10%.
When you have, but no, I'm trying to say this is only 10%. It's because of this issue of different free streaming length, or it's because CMB data are really crucial there, right? Because one is still relativistic at CMB decoupling, and some EV particle is not.
I'm not sure if we specifically tested which one. We can check offline, because we tested different galaxy surveys, so we might be able to tell how well they how well the galaxy survey matters versus the CMB survey.
Right, yeah.
That's a good question.
Other questions? If not,
Julian, sorry.
Yeah.
Can I?
Please.
Julian, I have a very naive question about your plot with the constraints as a function of spin. And you said that the scalar seems to escape somehow the data.
Yes.
And I do not know if there is any easy explanation for this, or
that's a good question. Thanks for asking. I was hoping someone would ask. I don't actually have a strong, the intuition is the scalar has smaller degrees of freedom, just lower energy density. So one possibility is that it barely escapes just because it's slightly below, it's like right below the threshold. But you get really good, very well close constraints for like everything else. So another explanation is that the data doesn't really want to rule out a scalar, because maybe there might be some, the data might want a scalar. But so the ellipse is not not exactly centered off of 0. This is the red ellipse for the scalar. So it just seems to be weaker by significantly at 2 sigma. And the 1 sigma, it's like maybe a little bit, the data doesn't seem to prefer having a scalar, but it has a hard time ruling it out. And it might just be because it's slightly harder to rule it out.